Howdy folks, welcome back to Advent of Code 2024. We are going to be looking at day 9. We got a bunch of pretty patterns going on here. I don't know what this is. It looks like a star is shooting something on the ground. And this looks a little bit like a runway. And this looks like something I don't really even know. But you know, it's pretty. Alright, disk fragmenter. Okay, we're amphibipods. Historians who pilot their amphipods struggling with computers trying to make more contiguous free space by compacting all the files. Why? We don't know. Apparently there's some reason we would do that. Shows you the disk map is already generated. For example, this. Dense format to represent the layout of files in free space. The digits alternate between indicating the length of a file and the length of free space. So 1, 2, 3, 4, 5 would be a 1 block file, 2 blocks of free space, 3 block file, 4 blocks of free space, and a 5 block file. Okay. And these have no free space because they're zeros. So alternating file, etc. Each file on disk also has an ID number based on the ID of files as they appear before they are rearranged, starting with ID 0. So disk map 1, 2, 3, 4, 5 has 3 files, 1 block, 3 block with ID 1, and 5 block with ID 2. Got it. Using one character for each block from the digits of the file ID and dot as free space, the disk map could represent these individual blocks, right? Because that's the free space. Okay, and here's those blocks. They would like to move blocks one at a time from the end of the disk to the leftmost free block space until there are no gaps remaining between file blocks. That's why they call this disk fragmenter, because when you actually defragment a disk, it does the opposite of what we're doing here. So in this case, this file is actually split into free space. It is a good way of compacting that free space. Realistically, if you're actually trying to get free space and leave your files unfragmented, you want to move these files. So you move 1, 1, 1 here, and then you'd stack 2, 2, 2, 2, whatever after it. But that's actually a much more time-consuming process. So this is a cheap and dirty way. And it's not, especially if you're on like a solid-state drive, it's not that much more expensive to do this. It was more, fragmentation was a bigger issue on spinning disks, mechanical, because if you had to move somewhere else on the disk to continue reading the file, you had to mechanically move the disk arm. Just some trivia for you. Okay, so they just move all this stuff. I don't know why. Why are we putting 9 there? Oh, from the end of the disk. Okay, so they just basically want to take the end and fill in. Oh, that's not as hard as I thought it was. They just want to basically take these and fill in all the free spaces whenever possible. And okay, and then update the file system checksum. Add the result of multiplying each of these blocks system with a file ID. Okay, so then this would be like 0 in file 0, 1 in file 0. This is 2 in file 9. Okay, so you'd multiply it kind of like that. Interesting. Okay, what is the resulting file system checksum? So we start off with here, and I think the first step, oops, that is not, would be actually to compute this string here. This would be pretty valuable because we would want to actually know so we can move these around and deal with that. And there's a couple that we could use an array. I guess really if you think about an array and a string are too different in the way that we're going to handle them. So we'll just handle it as an array then. Okay, so let's add our sample. Put it as a disk. Okay. We'll pull in this. Comes path. We'll pull in the path. Well, there goes. I really should just like. This is not required. This is actually going to be equals path dot join sample dot disk. I really should just have this, ready to go already. Just to read file sync. There we go. Okay, so let's see if we pull in these contents. We really need to go over them character by character because each one of these numbers means something. The interesting thing too is because these are single digits, we cannot have a file over 9 blocks or an empty space over 9 blocks. I wonder if that matters. Let's see. Well, it's disk equals, and we'll just make an array because why not? Current ID. Okay, so now we're going to for jar of contents. I think we can do this with a string. I think we can. That is really interesting, but not what I want. You know what? Actually, because I need to alternate between file, disk space, every odd character, well, no, because we start at 0. Every even character is going to be a disk block, and every odd character is going to be a empty space. Sorry, every even character is going to be a file block. I actually do want the index here, because then I can look that up really easily. This is going to be contents.length. And, okay, so then num, we know these are numbers, so we can actually just do a parseInt on it. Contents I. Okay. And then, okay, so if I 2 equals 0, so then if basically if it's even, which includes 0, by the way, 0 remainder 2 is 0, then we know this is a disk block or file block. Otherwise, disk block. So the disk then, for a file block, we're going to disk.push current ID, but we're going to do that less than for every block that we've got in our file. So if we get a 3, we push 3 of the current ID on, and then we increment that. If it's a disk block, then we're actually just going to push, let's use -1 to indicate empty space, right? Because 0 is a valid ID in this case, or a valid current ID. So let's see what we get. Okay, 0, 0. Okay, and then 3 empties. Okay, then 1. We've got 3 for 1. I don't know why is this showing up the way it's showing up? That's very weird. Thank you. Then we've got 3, 1. Okay, then we've got 3 of those. 1 for 2, 3, 3, 1, and then 2, 1. We've got 4 of those. Yeah. Okay, so that seems mostly correct. So then the idea is we want all these -1s to be at the end. So we could actually, I mean, if that's all we wanted, we could just do an inverse sort, or like a sort, and just push all those to the end. It'd be kind of fun to do. But we actually want to start from the end and swap with these positions. Okay, so what we're going to do here is we're actually going to do a double pointer system. So I want 2 pointers, one that starts at the beginning and one that starts at the end. This pointer is going to move forward. As soon as it finds a -1, it will actually swap these 2 positions, and that pointer will move back. So if we start here, we start 0, 0, -1, we stop, we swap that -1 to the end, we pull that 9 in here, and then this pointer will move 1 in. So that way we're continuously moving, and as soon as we get to the middle, then actually we're probably done. So I'm just going to set up a while loop with true for now. I think I will change that case, but start pointer is 0. End pointer is going to be our disk.length -1. We have to do -1 because, again, we're 0 indexed. So while true, we say, okay, num start item, just get start pointer. If start item, oh my god, I can't type, does not equal to -1, then we actually, oh no, if it does equal to -1, then we can do a swap. Okay, and at the end, we want to plus. And actually what we can do is we could actually say while end pointer is greater than start pointer. Because as soon as they become equal or less than each other, then there's no point in swapping anymore. Okay, now what do we do at this point? We assume that our end pointer is on a number, which maybe we shouldn't assume. Because what if they do give us something that's like this one is a specific, it's an odd number of digits. And so the last one is going to be a file. But if I put another one in there, well, that's certainly a thing that could possibly happen. So what we should probably do is at the very beginning is while end pointer equals -1. And yeah, there we go. So we're just going to loop at the very beginning of this loop. We say, okay, while the end pointer is pointing to -1, or is not a -1, excuse me, then we subtract. This might cause us problems in the end, but we'll see. So basically, if start item is -1, then we assume the disk pointer is not. And it is actually a number. So we're going to swap them. Disk end pointer. Disk end pointer equals start item. No. Pointer equals temp. And that it should be. Oh, fuck, I did this backwards. End pointer equals disk start pointer. There we go. There's the swap. Okay, so now that swaps. Okay, and then magically the start pointer moves forward. Let's just see what happens with this. Okay, it doesn't infinite loop. Doesn't do what it's supposed to be doing either, though. Oh boy. Okay, so let's see here. Oh, start item is a thing. Let's just see. Let's just print out our disk ahead of time. And then let's just see what happens. Okay. So first of all, 0 and 35. Cool. 1 and 35. End pointer equals just start pointer. This should have swapped though. Okay, let's take a look at our disk every time too. All right. So this is, yeah, that didn't do a swap. So that means my swap is, oh, that's why, because it's not -1. Okay, so as soon as I hit 2, then it should have swapped. So at this point, let's see, start item -1. Let's just do a check on that. Okay, so that is false, false, and true. Okay, so the next one should have that swapped, but it doesn't seem to be doing that. Let's see then. Temp gets the disk at the end pointer. Okay. Then end pointer becomes disk start pointer equals temp. Let's see what temp is then. Okay, so it's -1. Why is that -1? It shouldn't be -1. Oh. Oh, because of this. Wow, it's not equal -1. Oh, that doesn't make sense. That should do what it's doing. Disk at end pointer is -1. Really? Okay. That seems very unusual to me. Wonder if I'm running some weird JavaScript thing where it's just being silly. Yeah, okay. -1. Yeah, that's very weird. Because end pointer is 35. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay, so this is 10. Oh, yeah, 35 is not going to be the end of this then. Let's see, yeah, so maybe in the very beginning. Oh, it does. But this one is not equal. Oh, yeah, because I've actually to do this backwards. I don't want it to give me -1s. I did that completely backwards. There we go. So let's see, now it's 41, which makes sense. Okay, so now true. And now it should have swapped these, and it did. Cool. All right, so let's take these logs out and let's just see what it resulted in. Okay, here's the original disk. Here's the new one. That looks like that's mostly right. Like the 998, 888, 777, 6. All right, 6 is there. 6 has been pulled in there as well, and then we're done. That's it. Okay, so now that that's been done, we have to calculate the disk resonance or whatever. Checksum. Okay, so each one, the ID multiplied by the position. Okay, so that's going to be equals 0. So we're going to loop over the whole thing. Const block of disk. If block equals -1. Just skip over all those. Oh, you know what? I need the position as well. So I still need just length. This here. Disk of I. And then checksum is going to be plus equal I times block. I think that's it. Checksum is checksum. And let's see what we get. 1928, which is in fact what they say. Okay, cool. Let's try this on our input just to see if it works. Disk. Okay, that is a long string. Input. Okay, it's a big long number. Oy. Answer is too high. Okay. Okay. So, disk. What does that mean? Okay, I mean, that is a pretty high answer. I wonder if I'm calculating. Well, no, the checksum seems to be okay. All right. Okay, and that was, I think, what we ended up with for that one. I think. I'm going to run this over the sample again, just to make sure that our sample looks exactly like what they were expecting it to. Okay. There's 1/6 there. Yeah, I mean, that looks right. I'm missing here. Okay, a few more steps. That's all there. For disconnect, the process looks like this. Okay. First two blocks, okay, right, it's 0 to 0, 2 times 9, right, okay. And we did that. Checksum is the sum of these. Right, it's the sum of all these things. Interesting. How would we even debug this? Well, what we could do, potentially, is we could actually start looking at... Look at the first chunk of this, maybe, to make sure. Nah. Let's see, because there's a lot here. So there's 2,000 columns here, but we start with column 1. Oh, never mind, that's still not column 1. Column 1. Let's do this. I think it's WC. Let's see exactly how many. Okay, so there's actually... This is an odd number, which means it ends on a disk. So this is the last one. And this should be about 10,000, I think. This one. So this one would move to the front here. Let's just see what we get then. What is our final disk for the input? Oh, so it's 999. Okay, 999, 111. And then 4 slots open, which also become the 99 because there's 7 of those. And okay, and then there's one more, which, right, that works. And then the 8. I don't know. That kind of makes sense to me. So if our disk makes sense, is the way we're calculating the checksum's bad. Okay, as long as disk I, it is I times the block, right? Yeah, the position multiplied with the file ID it contains. Then 0, the block contains free space, skip it instead, which we should be doing. Line. So we're actually giving us different examples here, like a couple better examples. They're a little longer. I mean, like we have this one, right? Like we could use this one, see what it gives us, or 1, 2, 3, 4, 5, stuff like that. Well, let's see here. Okay, so basically OBS froze and didn't update my screen for the last 6 minutes of my recording. So we're just going to talk about part 1 again briefly. The bug that we found is that at the very last loop through, the end pointer would actually skip to before the start pointer. But because the while loop was still running that particular iteration, it would actually switch another number back, then finish and end the loop. So there was actually a -1 that was getting switched to one of the actual digits. What I did to fix that was I just made this a while true and put the condition inside the while loop after we get our next end pointer, and that fixed that problem. Nothing else really needed to change for that. So yeah, that actually fixed that and got us the correct input. We'll talk a little bit about the algorithm because that also got lost. So we're getting our contents in here. We're pulling this. We're filling up an array basically with our ID, our -1. Then we're using a double pointer method which runs an O of n time, figuring out where our first valid non-1 end pointer is. We're getting our start item. If the start item is -1, then we're just going to swap the two and increment the start pointer. So things should slowly be filling up that space. Then for the checksum, we loop through everything, skip our blocks, our empty blocks, and then multiply the rest. Now, part 2, the issue is they want to move contiguous file blocks. So not split them apart because the fragmentation is a terrible idea. So to do that, what I started off doing is I'm using just blocks on the array instead of actual just using a long array of numbers. I'm using arrays of blocks because it'll be easier to work over these and figure out if you have space very quickly. So now in our loop, we're just looping over the blocks, and if we find -1, we ignore it. And I'm probably going to do an n² loop here because I need to be able to loop through all my empty blocks to find one that will fill that space. So then what we're going to do, okay, is we're going to say, all right, you know, I'm interested in this one. Yeah, it should be fine. We're going to loop again. Not block size. This is going to be disk.length. I don't even know where size comes from there. Okay, so we're going to look through. We're going to find, and at this point, actually, we want to find anything j is greater than, is less than I. Okay, because we want to find a specific block. Oh, you know what? This actually should be at the end. This needs to be disk.length -1 greater than 0. Yeah, there we go. And minus greater than or equals 0. Because we actually are starting from the end and moving backwards for this loop. And this one is starting forwards to find an empty block. And so then here we're going to say if block ID is not equal to -1, then we break. If block size is less than oh, you know what? This should be disk j, and this should be block 2. If block2.size is less than block.size, then obviously we can't fit, so we're going to continue. If it does fit, okay, we have two cases. For one, we're going to take our entire block and we're going to move it to where j is. Okay, so we're going to do a splice here. Disk dot splice I 0 block. Okay. First, let's actually remove it. So disk.splice. We're going to go I and no, say it later. Okay. So we're splicing that entire block and we're just moving that to the disk. And now this block size needs to reduce. Equals, okay, this is going to be block2 size minus block.size, okay? If new size equals 0, if it equals 0, then we're actually going to remove our empty block, okay? This should actually be j. So that means at j plus 1, because remember we put this block at j now, j plus 1 is the new empty block. There are so many ways this could go wrong. We're going to remove our memory. Oops. Space. Okay, otherwise we're going to shrink it. Okay. Now, that new empty space, normally I would just throw that to the end of the disk, right? But I don't actually care about it. I don't need to do anything with it because I'm not using it to compute the checksum. So I can actually just completely throw that away and just assume, oh, it's at the end, it's empty. I think this will work. I'm interested to see what comes up here. And then let's just comment out this because this is not going to work right now. Like this loop will utterly explode. Let's do this on our sample and let's see what we get. 2. Okay, we've got ID 0, ID 9, size 2, that's perfect because that's what they recommended would be in there. And then there's block 2, okay? And then there's block 1, which is of size 3, block 7, no, block 9. Oh, because we're not removing, right, we're not actually removing our old block out of the system. So we're splicing it in here, but we actually have to disk.splice I1. We actually have to remove that block out of this point. All right. 9, so that's still in there. Because it's I plus 1 at this point, because we've actually, you know what, let's do that one first. No, it's still 9. 0 and 2. Why are we getting 9 twice when I should be getting 7? 7, 7, 7. Oh, because 7 is a size 3. But we had a block of size 3 there. What is our disk beforehand? Okay, so this one, there is a block of size 3 there. That gets taken up by the 9. But interestingly enough, that should not be good. Oh, and then the 2. The 9 and the 2 both take that up. Okay. And the 9 and the 2 take this one up as well, which they should not be doing. Oh, you know why? Because once we found a thing, we can break. That's the issue. It keeps on finding up spaces and filling them. Okay. Now we get the 7. Okay, so 7 and then 4. Okay. Oh, no, there should be an empty space there. Okay, so we do need to track the empties then. So where this is coming in, where this one's coming in, we actually need to make a new block and replace it with that I. Okay. So we actually need to replace this with a new ID -1 and size of block.size. This makes some things a little complicated because if there's empty blocks on either side of that, they might not work correctly. But the hope is we're going from the back forward, so maybe that won't be an issue. Because it's not like we're going to be putting things there. Okay, so let's see. Size 2. Okay, and then there's the 2, there's the 1, there's 7, there's an empty. Okay, then there's 4, then there's an empty. Not that. Then there's 3, and then there should be an empty of 4 blocks, but I think that's split up. So we've got an empty of 4. Okay, so yeah, there is 4. Then there's 5, and an empty. 6, then an empty. Okay, and then there's, what is this? 3, 4 empties. No, 5 empties, because we have that. And then there's, okay. And then there's an 8. and there's an empty that's got a size of 0. Okay. That's cute. Oh, probably. I wonder if this didn't work. It's not the biggest deal to have that in there. It's just kind of unclean. Okay. And then we've got like this 2 box. Okay. So that does actually look like that worked. Kind of. I really have many fears that that's not going to work well for the end times. But let's add the checksum calculation now. Okay, so block, this is going to be block.id. Okay, and now this is actually going to be block, oh, we need to do multiples. Okay, so, oh, this is actually going to be kind of a pain. Because every time we do a block, we have to increment our index. But so here, index plus equals block.size. And so for here, index I less than index block.size I plus plus. Then we need to add, yeah, that checksum like that, and this should increment. You know what? Let's just do this. Index less than, and then we can use index. You can actually do this with a for loop. It's just a little weird. Just not do an initialization statement. I think this will work. Oh no, it doesn't work. Of course it doesn't work, because we're incrementing the index constantly. Okay, that's fine. We'll just go with I then. Index, yeah, we'll just put that there. Okay, 2858. 2858. Okay, so then let's try it with, that's where everything is going to go wrong. Let's try it with our input. Okay, let's just see. Okay, I don't believe that worked. As you can see what happened in the last one, but okay, here we are. Let's look at our algorithm again. It's very different from part 1 because we need to do a very different thing. And sometimes that happens, right? With some of our other algorithms, we just needed a very small tweak. Some of them we need a very big tweak. So here we go. Instead of adding each number individually to the disk, we're using a block and just using IDs with it. Then we're looping over all these blocks, skipping these ones. If we find a block that actually has an ID, and we're going from the back forward, mind. As soon as we find a block that has an ID, we look for another block that is empty and can fit that block. Then we do a bunch of splices to move the blocks around appropriately and either remove empty space. We honestly could just do this as well. We don't need this empty space thing here. That's just for a little bit of cleanup so we don't have 0 blocks everywhere. Create empty space where the block was, move it to the new place, and reduce our existing empty block. So we're just kind of moving chunks around now, which it would have been easier to conceptually understand this if we were using the array of numbers, but it also would have been more code because we would have had to do a lot more loops to make sure we have space and stuff like that. Yeah, and at that point we can break because we did find something. And then the checksum is kind of similar. We're just keeping track of, this I no longer represents the actual point in the disk we are, so we have to use an index that we just increment every time we go over a block. All right, this was a fun one. A little bit of complication there in the first part, and also my OBS decided to crap out. So apologies for that. Hopefully I was able to still provide an interesting experience. Thanks for watching. I'll see you all next time.